So I'm going to talk a little bit about my Unit 10, where I cover electrostatics and DC circuits. I'm going to focus on DC circuits for right now, because these tend to be bigger parts of the FRQs, and these are a little bit harder to understand. So I think to illustrate a circuit, I want to talk about what's called a bucket brigade. This goes back to, and what I always think of are the old West towns where, like a schoolhouse, some wooden building is on fire. All the village people come out and to bring water, to haul water from buckets from like the well or from the pond to throw on the fire. So give me just one moment, and I'm going to make a couple of sketches here. So I have the pond, and I have our building on fire. I'm sorry I can't use color on my smartboard. I use really pretty reds and stuff like that. And when we have a bucket brigade, we have a line of people lined up, and they just pass the bucket from one person to the next. The last person throws the bucket of water on the fire. Empty bucket comes back and gets refilled, and they have a lot of buckets, so they're just going to continuously do this. So give me a second to sketch this in. So here's my line of people, and we fill up the first bucket full of water, and that bucket gets passed from person to person to person to person to person. Last person throws the water on the fire. Empty bucket goes back, gets refilled, and we continue the process. This is what I want my kids to have in mind when they're looking at a circuit problem, because this is how I introduce the idea of a circuit problem with this analogy, because here the pond represents my battery. It represents my energy source. And so since the pond has water, a battery has energy, the water in the bucket represents energy. And what we're doing is we're carrying some energy from the pond to the fire. The fire, in the case of a circuit, is my resistor. The resistor is that component in a circuit that takes energy from the battery, converts it to something else, light or heat, whatever. And so the fire needs the water, resistor needs the energy. In a circuit, the energy gets from the battery to the fire through the wires. Now, this actually gets a little bit more complicated, but what happens is the electrons in the wire pass on that energy along the line to get it to the resistor. So here the people represent wire. More specifically, they represent electrons in the wire. The water in the bucket is my energy. Well, we need something to carry water, and so we also need something to carry the energy. The bucket is our charge. The charge carries energy from the battery to the resistor. The energy of the water gets dumped on the fire. The energy gets passed on to the resistor. The charge comes back without any energy, gets refilled, and continues through. This is kind of the analogy that I want them to have in mind, and I still use it even in my E&M class. Let me go through a couple of terms here and kind of define things a little bit more. Let me draw the circuit analogy to what I just had: the pond, the people, and the fire. And our circuit analogy is we have a battery, we have wire leading to a resistor, the wire goes back to the battery. So this is my battery, this is my energy source, this is my resistor, this is the thing that's using the energy from the charge that's being carried to it. The battery stores energy. And when we talk about energy that's stored, that's potential energy. And the form of the potential energy is electrical potential energy. So the battery is a source of electrical potential energy. We're going to take this energy and convert it to some other form. Light or heat, that's what the resistor does. The charge leaves the battery with a certain amount of electrical potential energy, gets passed along the wire, loses no energy when it's being passed along the wire. This is one of the simplifying assumptions we make. The charge then has to go through the resistor. Now, in order for the charge to go through the resistor, it has to do work. So charge does work to get through the resistor. Work is a transfer of energy. So when the charge does work to get through the resistor, the charge gives its energy, it loses electrical potential energy, the resistor gains that energy, converts it to light or heat. So here, right before the resistor, the charge has a certain amount of electrical potential energy. Let's say it's 1.5 volts. It's a 1.5 volt battery. Right here, the charge has no energy. It used its all to get through the resistor. So our change in energy level is 1.5 volts. That's what we call delta V. The change in voltage, and that's real important to understand. Voltage is a real complicated term to understand. But what's happening is we're changing our voltage level as we get through the resistor. So we can quantify our resistance based on a value, and it's basically our resistance value, which is actually a pretty hard term to identify. But the unit, we quantify the amount of resistance with the unit called the ohm, which has the symbol omega. And then we can also look at how quickly the charge goes through the circuit. And so that's what's called current. Current is kind of the speed of the charge. Current is measured in amperes, and that's equivalent to 1 coulomb every second. Coulomb is our fancy word for the bucket, and I apologize for not introducing that earlier. So basically, a current of 1 amp is a bucket per second. I don't know how much energy is in that bucket, though. That's the kicker. The amount of energy is in our voltage term. And so the volt or voltage, it refers to the amount of energy in the charge, or the amount of water in the bucket. Refers to energy. When we talk about current, we're just talking about how fast is that bucket moving. We don't know how much energy is in that bucket. That comes from the voltage. And so the voltage, or 1 volt, is equal to 1 joule of energy. Here's our energy idea, per coulomb. Not all buckets are the same size. Not all charges are the same size. Some charges could hold more energy than others. And if you have a 5-gallon bucket, you don't necessarily have to have 5 gallons of water. And so our idea of how much water is being moved in this bucket, how much water do we have available, that's our voltage. That's our joule per coulomb. How quickly that bucket is being moved is our current, our coulombs per second. And then the resistor talks about converting the joules, the energy, to some other form of energy. I'm not going to break the resistance, the ohm unit, down, because quite honestly it's very complicated. But what's just simply most important is to realize the relationship between current and voltage. That's what the problems really dive into. I want to take another look at some of the terms associated with these circuits. And so first, let's begin with looking at what current is. Current, which has the symbol I, which is a little bit unusual, but it refers to the intensity of the flow of charge, or the pusher charge going through the line. The unit is the ampere, which or the amp, which is a lot of people call it, which is just simply given the symbol A. And what the current is I like to define it as the speed of the charge. If you think about our bucket brigade analogy, if I look at one person and I count the number of buckets that pass that person in a minute, that would be the current. Now, we don't use a minute, we use a second. And we don't use buckets, we use coulombs. And so a current of 1 amp is equivalent to a coulomb of charge per second. And we're looking at one point in our circuit, and that's kind of important to recognize. So what the current simply tells us is how fast our charge is moving. What we don't know is the amount of energy in that bucket. That comes from voltage. Voltage is a confusing unit because it's usually used incorrectly. Like we say, a battery has a voltage of 1.5 volts or 3 volts, and that's actually incorrect. That's not the voltage. What that actually referred to is the difference in the voltage. So the symbol for voltage should be delta V. How much does the voltage change? When a charge goes through a battery, its voltage level, its energy level changes by a certain amount. When a charge goes through a resistor, it loses some of the energy. Its voltage will change by a certain amount. And so this is pretty important to recognize the difference between current and voltage. And I get it. The unit for voltage is the volt, which is symbolized by V. I get the confusion, and I'll be honest, I use V instead of delta V a lot of times, but that's a bad habit that I'm trying to fix. I like to refer to voltage as related to the amount of energy. It's related to energy. Basically, voltage is how much water did we put in our bucket, or how much water did we throw out of our bucket. That's kind of what it's related to. 1 volt is equivalent to 1 joule per coulomb. Back to our analogy, energy is water. Coulomb is our bucket. So the volt tells us how much energy is in our bucket. How much energy is this charge carrying? When a charge leaves a battery that is 6 volts, it has 4 volts, 4 joules per coulomb. The last unit that is often comes up is what we call resistance. Resistance has the symbol capital R. The unit is the ohm, named after, and I don't remember his first name, his last name is Ohm. And the symbol that we use for the unit is not capital O, because that would be confused with 0, but it is capital Greek O, which is omega. What the resistor does is that it converts electric potential energy into some other form, light, heat, whatever. So I'm just going to say light. A light bulb is a resistor. As I mentioned before, it does this because the charge has to do work to get through the resistor. So the charge gives up some of its electric potential energy. The resistor uses it as light. Another term that comes up often as we look at these problems is the power. We talked about power before with mechanical power, and it was the rate work was done or the rate energy was used. it's the same definition here. Power is, one way to calculate power is simply taking current times voltage. Current is coulombs per second, voltage is joules per coulomb, and so we end up with joules per second, which is our unit of the watt. Now we can also, and so here you see, here's where I kind of went a little old school. I miswrote that power calculation. What I should have written it as was I times my voltage change. This is why, this is what you should be careful about. Now, another relationship that comes into play, and I might have mentioned before, is what we refer to as Ohm's law. Ohm's law relates our voltage change with current and resistance, and Ohm's law says delta V is IR. This is used a lot, and here's the thing with Ohm's law. We can apply this to a specific resistor in a circuit, or we can apply it to a group of resistors, or we can apply it to all the circuit. So this is applicable to individual resistors, and I'm just going to abbreviate as R, to the entire circuit. It's a very, very powerful tool. I can take my expression for Ohm's law, substitute in for delta V. Another way to express power can be I squared R. I could rearrange Ohm's law for current, substitute in delta V over R for I, and get yet another way to calculate power, which is V squared over R. The method that you use is going to be kind of dependent upon the information that you're given. Kind of like Ohm's law, we can apply the power to the power dissipated, the amount, the energy, the rate energy is used through a single resistor, or to the entire circuit. These are pretty powerful, no pun intended, these are pretty powerful expressions, and you have to be careful when you're using them because they can be used in a lot of different ways. I want to take a quick look at two ways that resistors can be configured within a circuit. They can either be in series or they can either be in parallel. Now, the problems that we will encounter will be a combination of the two. Some resistors are in series, some are in parallel. And so you have to kind of take a little bit of information from series, a little bit of information from parallel, and go back and forth as to when you do the analysis. I'm only going to look at series, and then I'm going to look at parallel. So a series circuit, I like to say a series circuit is resistors one after another. The charge has to go through resistor 1 in order to get through resistor 2. So I'm just going to say 2 consecutive resistors. It could be more, it could be 3, it could be 4, it could be 100. So we have a battery. That's our symbol for resistor. This is our symbol for resistor. We return to the battery. So this is my voltage source. I'm going to call that R1. I'm going to call that resistor 2. So this is when resistors are in series, this is what I meant by 2 consecutive. A charge leaves the battery. It gets to the first resistor. It has to do some work to get through the first resistor. Because it does some work, it's going to experience a voltage drop across this resistor. If it leaves the battery with 6 volts, it's going to have 6 volts here. It might have 4 volts here. And so we had a voltage drop of 2 volts. the charge is going to get here over the second resistor, and it's going to give up, it's going to have another voltage drop, but it's going to give up the rest. The charge returns to the battery at 0 volts. It's just the way it is. It gets a little complicated as to why that is, and it gets a little complicated as to how does it know how much energy to use. That's where Ohm's law comes into play, looking at the current, and so those are some practice problems that we have to just simply do. But it has 4 volts here, it has 0 volts there. And what we know with a series, it's going to give up, this is like 2 house fires. I'm going to put a little water here, I'm going to put the rest there. And so our overall voltage is simply going to be equal to the voltage drop across resistor 1 plus the voltage drop across resistor 2. The current, and this is the current, this is how fast the charge moves through the entire circuit. The current will stay the same. The current through resistor 1 is the same as the current through resistor 2, which is the same as the current through the battery. Notice I'm saying the current through, the voltage drop over, across. Voltage drop requires 2 points. Current only requires 1. We can simplify this circuit to a circuit with a single battery and single resistor. This overall equivalent resistance is equal to the 2 resistors added up. And this equation is similar to one that's on the formula sheet. So let's look at the other type of circuit, or the other type of arrangement resistors can be in, and that's parallel. We can recognize a parallel circuit when the charge is going through the line and it splits. That is, the line splits. The charge has a choice. I can either go that way or I can go that way. And when the charge is given a choice, that's a parallel circuit. And so, parallel line splits. Line splits to 2 different resistors. Sometimes parallel circuits can be difficult to recognize because the resistors aren't literally parallel. Let me give you an example. We have a battery, we come out, we have a resistor, and we have that type of situation. We have this, so the charge leaves the battery, it gets to this junction, and it can go through either resistor 1 or it can go through resistor 2. It has a choice. It will not go through both. It's only going to go through one. And whenever it has the choice, that tells us that resistor 1 and resistor 2 are in parallel. And so the charge goes one of the paths, gets back to here. So if we have 6 volts here, the charge has 6 volts there, goes through either R1, where we have a voltage drop, or it goes through R2, where we have a voltage drop, gets to this point, has 0 volts, because it returns to the battery with nothing. And so one of the unique things, or one of the interesting things about parallel circuits is that the voltage drop across resistor 1 is the same as the voltage drop across resistor 2, which in this case is the same as our battery voltage drop. Not the same as with resistors, with series. This is kind of similar So this is kind of similar to a grocery store checkout line. It doesn't matter whether you go through line 1 or 2. You're going to spend the same amount of money. The charge is going to use the same amount of energy to get through that branch. One branch might be quicker, but that's another issue. And so that's, if it's quicker, then that's where the current is different. And so what we see in this case is that the current through resistor 1, this charge has a certain current right here, which I'm going to call the battery current. Right here, it's going to have a current that is however fast it goes through resistor 1. It has a current however fast it goes through resistor 2. And then it rejoins down here to be the battery current. And so what we see is that the battery current is equal to I1 plus the current. The currents add up. The voltage drops across each branch is the same. Just the opposite as with a series circuit. Very important to understand these characteristics. Just like what I did with the series circuit, I simplified this to a battery and a single resistor. This overall resistance is a much stranger calculation. And basically what this overall resistance is, and I think it's expressed this way on the formula sheet, it's 1 over Rp is equal to 1 over R1 plus 1 over R2. In other words, our total resistance, our overall resistance, is 1 over R1 plus 1 over R2. This has interesting implications because Rp, our overall resistance, is less than our individual resistances, I guess is what you say. So Rp is going to be less than R1 and Rp is less than R2. These characteristics with series and resistors in parallel and how we lower resistance, is what's critical to understand. I now want to take a look at a circuit that has combination, series, and parallel. These are going to be more similar to the problems that we're going to run into. So here's our battery. I'm going to call this resistor 1, resistor 2, resistor 3, resistor 4. And what you got to recognize is that some of these resistors are in series, some are in parallel. For example, R2 and 4 are in series. R3 is parallel to R2 and R4, which are in series. R1 is in series with this whole section. So to analyze it, you have to break it down into parts. What I like to do is to simplify it down. So this circuit can be simplified down to, this is R1, this is R3, and this is R2 plus 4. Now I see these two are clearly in parallel. And so we can simplify this down further to where this is R1 and this is the equivalent resistance of those two in parallel. And you have to break it down into these individual steps, otherwise you're not going to be successful in doing the problem. You have to recognize that the current through these two is the same. The current here is the battery current. And so this is current 3. And so what we have is the battery current is current 3 plus the current through resistor 2 and 4. What you have to recognize is that this voltage drop is equivalent to the voltage drop across resistor 2 and the voltage drop across resistor 4, because these are in series and the voltages add up. And so, with a relatively simple circuit, and the circuits that we analyze will not be much more complicated than this, there's a lot of relationships that you have to keep track of. When resistors are in series, their voltages add up, their currents are the same. When resistors are in parallel, their voltage drops across each branch is the same, the currents add up. And it takes practice doing these problems, because the questions you get aren't necessarily going to be analyze it through the math, but tell me what happens if this resistor fails. What happens to those other two? Where does the energy go? If these are light bulbs, do they get brighter? Do they get dimmer? That's the type of question that you have to be able to analyze. These problems can get complicated. They take a lot of practice. You have to keep in mind those characteristics, that's the difference between series and parallel. That's the key to all of these doing all of these problems. A couple of things to keep in mind when you're analyzing these problems. Keeping in mind there is a big difference between our voltage drop and current. You have to understand and be able to explain the difference. Kids a lot of times have trouble with that, kind of similar to with them understanding the difference between velocity and acceleration. Big difference between those two terms. Big difference between voltage drop and current. You have to be able to apply Ohm's law correctly, whether at a specific resistor or a specific branch or the entire circuit. Similarly, you have to be able to look at the power, the rate energy is dissipated, and that's the wording they use often. Again, at the individual resistor or the entire circuit. You have to understand the characteristics between series and parallel resistors. It's not so critical as to be able to analyze this big, complicated circuit. It's critical where you have to recognize these resistors in series, the voltages add up, the current is the same, what's happening with the current when it reaches parallel. You have to be able to explain that using the language of physics. That's why kids struggle with this. It's typically the last unit. People typically go through it really fast, and it's hard to get it to the level that the kids really need to understand to answer some of these FRQs that are put to them. But if you keep in mind the bucket brigade analogy, how energy is moved, because that's what the questions come down to. How is energy moved from the battery through the various parts of the circuit? And then what happens if part of the circuit fails? Where does that energy go now? That's the type of questions you're going to have to be able to analyze. I hope this has been some value to you. Good luck.